Hi, my name is José Cambronero, and I'll be presenting our paper titled AMS Generating AutoML Search Spaces from Weak Specifications. This is joint work with Jürgen Cito and my advisor, Rinard. If you're a software developer looking to build a supervised learning system, you have already encountered or will soon have to implement a machine learning pipeline. In this setting, a machine learning pipeline goes from labeled data all the way to your trained model. In between, there are certain key steps, such as choosing hyperparameters, scaling your features, feature selection and extraction, and so on. These pipelines are typically implemented using third-party libraries. A common example of this is the Python machine learning library, scikit-learn. So now, if you're a developer and you need to write a machine learning pipeline, what options do you have? If you think of machine learning expertise as lying on a spectrum, on your left-hand side, you have experts with their expert machine learning knowledge who may be inclined to manually implement and validate their own pipelines. On the other end of the spectrum, you have people who are not experts in machine learning. They may be inclined to use a technology such as automated machine learning, commonly termed AutoML. Usually a search system that will produce a lot of different pipeline options, prune them down, and identify ones that have good performance for your dataset. So there are both pros and cons of the manual and the AutoML setting. On the manual end, you have a high degree of control, but this requires expert machine learning knowledge, and it is time consuming for the developer not only to implement the pipeline, but to validate the choices they've made, which include the architecture, the operators, the way they're composed, and their hyperparameter settings. You have to decide whether or not those will actually perform well for your specific dataset. On the other end of the spectrum, you have automated machine learning, where you have lower degree of control, but you don't have to have expert knowledge, and it reduces developer time. In practice, lower degree of control means that a lot of automated machine learning systems will produce pipelines that are not what you desire. For example, you may be interested in having a pipeline that only uses linear classifiers, but in the end, the AutoML system may very well produce pipelines that all use ensemble-based tree models. So what this means is that there are people in this middle ground in the expertise spectrum that have some amount of knowledge. They know what they want in terms of a pipeline, but they don't know how to communicate it to an automated machine learning system. And this is where AMS comes in. AMS seeks to harness the developer's knowledge of what they want in a pipeline, automatically augment it, and provide it to an AutoML search system so that the pipelines that are searched more closely align with what the user wants. In order to understand how AMS influences the pipeline search, we must first introduce a key player, the machine learning pipeline search space. This is the set of all pipelines you can obtain when you compose operators in different ways, set hyperparameters with different values, and so on. The first thing to note is that this is an extremely large set of programs. So you as a user may want to use an automated machine learning system to efficiently search this space. In this case, the AutoML system searches within this blue rectangle and considers programs that come from this part of the space. The blue rectangle is defined in part by the operators that the system designers considered were relevant for their search procedure, and then the search procedure itself. So for example, this AutoML system may be focused on producing pipelines with tree-based ensemble models. However, you, as a user, may have a different notion of what's desirable. In this case, this orange box only partially overlaps with what the AutoML system would initially consider for search. So in this case, say you're interested in pipelines that mainly contain linear models. So the goal of AMS then is to allow you to provide some amount of partial knowledge, which we can then take, automatically augment, and use that to highlight a subset of the search space and focus our efforts there. To carry this out, AMS uses the following 5 steps. First, the user provides a set of API components that they think may be relevant. This constitutes the initial weak specification. Next, AMS adds components that could be used to replace some of the components that the user has initially specified. So this could be a different type of linear model to replace the initial linear models that the user specified. As step 3, AMS then adds complementary API components. These are components that may help improve performance or benefit in some way the components that were initially presented by the user. So for example, you might want to add a component that scales values before the main learning algorithm to improve convergence. As a fourth step, AMS then populates a set of hyperparameters and values that can be chosen for each of the components in the current specification. And finally, AMS pairs this specification so far with a user-chosen search procedure that will then fully define the search space. Let's zoom into this workflow and understand each of the steps. So as the first step, we said the user provides a set of API components as a weak specification. So in this case, the user knew they wanted a linear classifier, and they know that logistic regression is one such classifier, so they can provide AMS with a single component specification that states logistic regression as a possible component to include in a pipeline. As a second step, AMS now adds alternative API components. AMS finds components that could be used to substitute the ones provided by the user in the original specification. These are components that will provide more or less the same functionality, but have potentially different properties, such as faster convergence or robustness. So the key insight here is that we can use component descriptions to identify those components that we think are substitutable for them. To do this, AMS relies on API documentation. So it uses information retrieval over natural language descriptions of each of the components to identify those that are related. So for example, in this case below, we'll see the natural language description for scikit-learn's logistic regression. Using the initial documentation for components in the original specification as a query, we can retrieve components that are then relevant, related, and can be used to substitute those in the original specification. So in this setting, a document is a potential substitutable components documentation, a query is an existing components documentation, and a corpus is the complete API documentation for the relevant target library. And we use an information retrieval scoring technique called BM25, which scores each document, so each potential substitutes documentation, with respect to a query, in this case an existing components documentation. And this score is not only a function of the document itself, but the broader corpus. So for example, in our original specification, the user may have specified logistic regression, which is a linear model. In this case, we could also substitute it for a different linear model, in this case, a linear support vector machine. The third step in the AMS workflow consists of adding complementary API components. These are components that, when jointly used with some in the original user specification, may improve performance. So for example, you may be interested in scaling your feature values before handing off your dataset to your core learning algorithm. A key insight used for AMS is that useful components will tend to appear together in existing code. So AMS will use a corpus of existing source code, and we will look at the different components used in a script and identify, for example, that min-max scaler, a feature scaling algorithm that limits values to lie between a minimum and a maximum, is used jointly with a support vector machine. To formalize the idea of these complementary components, AMS relies on pointwise mutual information. So in this case, if X and Y are both different components, the intuition is to find out if they appear together more often than expected if they were independent. Formally, is the joint probability of the two components higher than the product of their marginal probabilities? We then normalize this pointwise mutual information to lie between -1 and 1, such that any components that have a pointwise mutual information above 0 have higher degree of correlation than if they were independent. And we'll go ahead and build a set of association rules based on this pointwise mutual information, such that we can retrieve components that have some association with those already in the original user specification. So to go back to our example, where we started off with logistic regression, had already added linear support vector machine, we can now add 3 complementary components. Polyfeatures, which extracts polynomial features from the existing feature set. Min-max scaler, which will scale your features to lie between some minimum and maximum. And variance threshold, which selects features based on a minimum variance. Next, AMS must populate the set of hyperparameters and values for each of the components in the specification. As we all know, different algorithms have different hyperparameters to choose and tune. For example, if you're interested in clustering, you may have to choose the number of clusters. You may also want to do things like regularize your pipeline, so you'll have some regularization method, and you have to pick what kind and what weight to put on it, and so on. The insight for AMS is that user code will tend to set and explicitly tune hyperparameters that are useful. So if there are hyperparameters that are not particularly often tuned, we may assume that their default values work well, and we shouldn't worry about them in our own specifications either. So once again, AMS relies on existing source code, and in this case, it'll identify the set of hyperparameters that users tend to tune and corresponding values. So to populate our current specification with hyperparameters, AMS just has to count. It can go back to the code corpus and identify the hyperparameters that tend to be tuned the most for a specific component and the values that it tend to draw. So now our specification has grown from simply containing API components to specific hyperparameters and their possible values. As a final step, AMS pairs the current specification with a user-chosen search procedure, now fully defining the search space. In its current implementation, AMS exposes two different search procedures: genetic programming carried out by a third-party library, Teapot, and random search. And you could, of course, imagine incorporating different additional search procedures. So now what does this get you in terms of performance? First, let's discuss the concept of a pipeline win. Given n systems, each of which produce different pipelines, we can pick the best pipeline for each system based on the F1 score on a held-out test set. We can then compare all of these best pipelines, and we can say that system K wins this specific iteration if it has the best pipeline and its pipeline has an F1 score at least 0.01 larger than the next closest pipeline. So our first comparison is with an existing AutoML tool that we previously built, which learns from existing source code. AL, like other existing AutoML tools, gives users limited control over the pipelines produced, while AMS exposes control through weak specifications and their augmentation. So in this specific setting, AL will basically give you pipelines that it thinks are useful, but that may have no relation with what the user necessarily wants. To evaluate this, we carry out the following experiment. We use 9 datasets, 5-fold cross-validation to generate a total of 45 pipelines for AMS and AL. And we provide this user specification: logistic regression, linear support vector machine, and standard scaling. So now here we can see that AMS and AL have roughly the same amount of wins, and there are a small number of ties. However, AL does not use the specification in any form, because it was not designed to do that. It simply provides pipelines that are high-performing as it generates them, but never considers what the user necessarily wants. In this case, we can see that AL wins can be broken down into a large portion of ensemble models, tree-based pipelines, and then a small set of AL wins that do indeed come from pipelines that adhere to the user specification purely through chance. In contrast, AMS produces pipelines all of which adhere to the specification, and once we remove the non-specification adherent AL pipelines, AMS has 42 wins. Next, we carried out additional performance evaluation, considering other choices users might have to produce spec adherent pipelines. So in this case, the comparisons are amongst the following systems. First, we use the weak specification as a pipeline directly. Next, we can use the weak specification as defining a search space and layer search on top of that. Next, we could take the weak specification, and then for each API component, we can identify the hyperparameters and a set of values defined by experts that are worth tuning, and we can layer search on top of this. And then finally, we can use the AMS produced search space and then search within this space. For these experiments, we generated 15 weak specifications by composing popular components from the scikit-learn library. This included 3 different classifiers and 4 preprocessor components. We carry out these experiments on 9 datasets, providing 5-minute search budget for each iteration and carrying out 5-fold cross-validation. Our results are as follows. You can see that weak spec actually provides on its own a small number of wins. This can happen purely through chance, where those happen to be highly performing pipelines and that outperform those produced by other systems, but these are a relatively small number. Next, we can have weak specification plus search, and that improves wins slightly. Those increase yet again by using the expert-defined hyperparameter search space. And finally, you can outperform all these systems by using the AMS-defined search spaces. And the AMS pipelines are generated from a search space that reflect the initial specification. So here, for example, we have a specification from the user that states polynomial features, min-max scaling, variance threshold feature selection, and random forest classifier. Here's the distribution of components in pipelines produced by searching the AMS search space. We see, for example, that the top three classifiers, extra trees classifier, random forest classifier, and gradient boosting classifier, are all related to the random forest classifier in the user spec. They're all tree-based ensemble models. Next, the user provided a min-max scalar in their specification, and we see that the distribution of pipelines contains min-max scalar indeed, but also two other types of scaling, max absolute value scaling and standard scaling. Finally, the user provided a variance-based threshold feature selection component, which is included in the distribution of components in pipelines generated from the AMS space. But additionally, there's another feature selection component called select percentile that selects based on a percentile score for each feature. In the paper, we feature additional results, including precision for functionally related component retrieval, precision for complementary component rule mining. We characterize the hyperparameter use in our code corpus, and we analyze the impact of varying the corpus size, among additional results. In conclusion, we've presented AMS, which provides a new model for interacting with automated machine learning systems. In this setting, users provide partial information in the form of a weak specification of API components. This can then be automatically augmented and used to generate a full search space, which can be used to sample pipelines that reflect the influence of the original specification. Thank you.